Hey, this is Horner. We're going to look at the photoelectric effect. So the first hints about the photon nature of light came with a discovery that they did when they were using an electroscope and they had some UV light shine on that electroscope. When the UV light was incident on this little ball on the end of the electroscope, when they removed the UV light, they noticed that these two charged plates would actually come together, which means that they've got to be losing the charge, or the charge has got to be moving away from the ends. And what they finally figured out was that the UV light was exciting the end of this metal sphere, and it was ejecting electrons coming off of here. And as you eject those electrons, then we end up removing this negative charge from the electroscope. And that's kind of how we first thought, ooh, something's got to be going on here. This is our photoelectric effect experiment. And this is the device that we've talked a little bit about. So here we've got a window where we have light can come in. It hits some sort of metal on this side. Electrons are ejected, and then they complete a circuit, and we're able to kind of read the current. And then if I want to, I can adjust the voltage here. And if I adjust the potential difference, I can then measure the stopping potential and all kinds of other things that come along with the device itself. So when UV light does shine on the cathode, there's a steady stream of these electrons that are ejected, completes the circuit. If there's no current and the electrodes are in the dark, the electrons don't spontaneously kind of leap off that cathode. Um, and so we've got to make sure that there's light hitting this in order for it to work. Like we said earlier, the battery just establishes an adjustable potential difference, and with it we can study how the current varies with potential difference, and the light's wavelength and intensity are changed as we go through. So the photoelectric effect actually has the following characteristics. The current is directly proportional to the light intensity. So if I double the light intensity, I also double the current. The current appears without delay when the light is applied, and electrons are emitted only if the light frequency exceeds this threshold frequency. So it has to have a minimum frequency in order for the metal to have enough energy to eject electrons. That value, that threshold frequency, depends on that type of metal. So remember, sodium does it pretty well, copper does not. If the potential difference is more than about a volt, the current changes very little if I increase the potential. If that potential is made negative by reversing the battery, the current decreases until it stops, essentially, and that current reaches zero. So we can call that V-stop value then the stopping potential. The value of the V-stop is the same for both weak light and intense light. A more intense light just causes larger current, but in both cases that current ceases whenever that change in potential is equal to that stopping voltage, so I just don't get any ejected electrons. So here's a good example of what we can see. No matter how intense the light up to this threshold frequency, I don't get any current, and then suddenly at this threshold frequency I do get it, and then it kind of tails off as we go through. This is a diagram that is commonly used. We have weak light gives us a less current than an intense light would give us for the same frequency of light and for the same metal, and we can see where the stopping potential is. And notice the stopping potential is the same for both the intense and for the weak light. No current flows if that change in voltage is less than the stopping voltage itself. So in the experiment, current is detected when ultraviolet light shines on a metal cathode, and they want to know what is the source or the cause of the current. And obviously, it is that light that's coming in. It's hitting the cathode and ejecting electrons. So it's not the cathode itself, it is the light coming in, and that is giving the source or the cause of that current. Without that, you wouldn't have it. There is a minimum energy need to free from electron from a metal. So to get it out of there, we have to increase the energy until it has enough speed that it can escape. The minimum energy needed to do this is called the work function. Now, this text uses E naught for work function. Other texts use this symbol for work function, and other books use this one. I think this is probably the more common. Some electrons require energy that's greater than this energy to escape, but it needs at least this amount of energy or that work function for those electrons to be kicked out. Here are different work functions for different metals. We said sodium was probably one of the better ones, so it doesn't need much energy. Potassium is the same way. Once we get up into some of these more common metals, you'll see that the work function jumps pretty quickly as it goes through. An electron with energy E electric is inside metal, and it loses energy delta E as it escapes, so it emerges as an electron with a certain amount of kinetic energy. So this is the energy of the electron minus that change in energy, and the work function is just the minimum energy needed to remove an electron. So the maximum possible kinetic energy of an electron is this. If these two are the same, we don't have any kinetic energy. If you get a little bit more of this electron energy, then that electron can be kicked out, and it does have some sort of kinetic energy we can measure. So in the experimental device we used to study that photoelectric effect, those electrons, after leaving the cathode, move in all kinds of directions. And we want them to hit that anode, and if the potential difference between the two is equal to 0, there's no electric field between the plates. So some of the electrons will reach it, creating a measurable current, but many of them do not hit it. If the photoelectric effect measuring device in this device, if the anode is positive, so if I make this positive, then all of the electrons want to jump towards it. So no matter which direction they're initially going, they all find out that they're very attracted to the positive end. So we're going to go ahead and put the positives on this side, and we know that this is the cathode. And that increases the current. So you can actually make them move a little bit quicker. We get more energy and we'll get more current as it goes through. In the photoelectric effect, if I flip that and I make this side more positive and I make the other side more negative, then I won't have any of these electrons really ever hardly reach the end. So all of the electrons should get, they could get close to, but they're going to come back and hit that plate again. So just a couple of different ways that you can charge those two plates. We can use the conservation of energy to relate the maximum kinetic energy to that stopping potential. So electrons will convert kinetic energy to potential energy as they slow down. So when the change of potential is equal to that stopping potential, then the current ceases and the fastest electrons are just being turned back. 100% of their kinetic energy is converted back into potential energy. So here we say that the stopping potential is equal to the maximum kinetic energy divided by the elemental charge. So if we measure the stopping potential, that tells us the maximum kinetic energy of the electrons themselves. So here we are with our experiment again. In this experiment, a current is detected when UV light shines on the metal cathode. What happens to the current if the battery voltage is reduced to 0? So if it's reduced to 0, then the current decreases just slightly because we're not adding that positive charge on this side anymore. Einstein, and this was his baby. He made history with it. He was able to win the Nobel Prize. So we want to know, why did the electrons leave the metal? So the first explanation was that you were heating the metal. But the problem with that idea is that electrons began to leave as soon as light was hitting that metal surface. So you didn't have to warm it up for any amount of time. So the heating hypothesis also failed to explain that threshold frequency. We had a strong intensity at a different frequency, should be able to heat the metal, yet that experimental evidence shows that a sharp frequency threshold. So it didn't matter how much you heated it with a frequency that didn't eject electrons, it still would not eject those electrons. So Einstein explained that photoelectric effect by extending the work of a German physicist. His name was Max Planck, who had found that he could explain some sort of the form of the spectrum of a glowing incandescent object only if you assume that the oscillating atoms inside the heated solid vibrated in a particular way. So he said that these vibration energies for each one of the different energies was quantized. So here we've got energy can be 0, it can be HF, 2 times HF, 3 times HF, where H is Planck's constant. And remember, this constant can either be in joule seconds, or this constant can be in EV seconds. And you'll notice the huge difference between the two, since this is a pretty normal value and this is extremely small because of the size of an electron. Einstein suggested that electromagnetic radiation itself is quantized. So light really isn't just a continuous wave, but instead it comes in small little packets or bundles of energy, and we call that a light quantum. He said that the energy of one of those is directly proportional to the frequency, and so each quantum of light or photon has an energy, E is equal to hf. So the higher the frequency of light, the bigger the energy that it will have, and the higher frequency photons that it has. So in the photoelectric effect experiment, they want to know, why does red light not cause an emission of an electron that blue light can? And that's because the photons of red light don't have enough energy. So remember, ultraviolet is the strongest, and so that's over on this side of the spectrum. So this would be UV. On the other side is infrared, and then this is Roy G. Biv, red, orange. So this would be red, orange, yellow, green, uh, blue, indigo, violet, and then ultraviolet. So this is high energy, and this is low energy in comparison. So the photons of the red light don't have enough energy to eject the electron, but that blue light probably does. And we've seen that in the lab. Ultraviolet light at 290 nanometers does 250 times as much cellular damage as an equal intensity of ultraviolet at 310 nanometers. So there's a clear threshold for damage at about 300 nanometers. They want to know, what is the energy in EV of photons with a wavelength of about 300 nanometers. So here we're going to use E is equal to HF. We've got to find the frequency, so we're going to take the speed of light and divide it by the wavelength, and we end up with 1 times 10 to the 15th. So if we use our E is equal to HF, here we're going to use H and EVs times a second, and then our final energy here is 4.14 EVs. This is pretty reasonable. If I want to split a water molecule bond, it takes about 4.7 EV. So for energies larger than about 4.1, photons can really just wreak havoc on the genetic material cells. Lower energies really don't have much of an effect at all. Einstein did have some postulates for the photoelectric effect. He said that light of frequency F consists of discrete quanta, or just a packet of energy, and that's E is equal to HF. And each one of those photons does travel at the speed of light, and remember that is C. Light quanta are emitted or absorbed on an all or nothing basis, so it can either emit 1 or 2 or 3, but not 1.5. So it can only do whole number integers. Similarly, an electron in a metal can absorb half, but only 1, 2, 3, and other whole number integers. So the third thing, a light quantum, when absorbed by a metal, delivers its energy to only one electron. So when one packet of light comes in, and it comes into a metal, it only will affect one atom, and it will only give its energy then to one electron, as that electron is jettisoned off because of the energy that is picked up. His postulates have, if you apply them to the photoelectric effect, just say that light shining on a metal, each one of these photons has that energy HF, and each photon is absorbed by one electron, and then we have the energy of the electron, which is equal to HF also, since the energy going in needs to be the same as the energy going out. So an electron can escape from a metal if its energy exceeds the work function. And there's a threshold frequency for that. So this is the work function divided by Planck's constant. If that frequency of a photon is less than the threshold frequency, there aren't any electrons that have enough energy to escape. Weak light with a frequency greater than or equal to that work function will give just a few electrons, because each photon delivers all of its energy to just one electron. So this is exactly what the data shows with that threshold behavior. The more intense light gives a lot more. Very little light does give some, because remember, each one of the frequencies, each one of the packets of energy goes to just one electron. A more intense light delivers a larger number of photons, they eject a larger number of electrons, and do cause a larger current. So that's exactly what we've kind of seen in the labs. If I go through the there is a distribution of kinetic energies because I have different electrons require different amounts of energy escape, but the maximum kinetic energy here is just K max, and that's the energy of electron minus the work function, or HF, minus the work function itself. His theory predicts that the stopping potential is related to light frequency using this equation. So here the stopping potential is the maximum kinetic energy divided by E, and we define kinetic energy using using the above here. So it's just HF minus the work function all over the value for the elemental charge. So the stopping potential does not depend on the intensity of light. It just gives us more current. If each photon transfers its energy HF to just one electron, that electron immediately has enough energy to escape, and the current does begin instantly. No delay at all, don't have to warm anything up, just kicks it right out. We can think about a swimming pool. If you throw a pebble in a swimming pool, that pebble will go in, but all it does is it just causes the water to ripple. So that's the classical way of looking at it. If we look at it and we say that all of the pebble's energy goes into one drop of water, it's going to kick that drop of water clear out of the pond, and that will come up onto the surface. And so that's kind of the same thing that we're doing is we're taking light coming in, it's only hitting one water drop and it's popping that water drop back out. Einstein did win the Nobel Prize in 1921 for this big explanation of the photoelectric effect. So if we have monochromatic light, that's just light of one color like a laser, shines on a cathode in a photoelectric effect experiment, it causes electrons to be kicked out. If the intensity of the light stays the same, but the frequency of the light is increased, will there be more electrons? Will the emitted electrons be moving at a higher speed? Are both true or neither true? And here, what's true is the emitted electrons will be moving at a higher speed because they will have more energy. Second thing, same thing, but this time if the frequency of the light stays the same but the intensity increases, then there will be more electrons emitted. Okay, so they won't be moving at a higher speed, they move at the same speed, we just have more of them. So that's the difference between the two. They want us to figure out what are the threshold frequencies and wavelengths of the electron emission spectrum for sodium and aluminum. There is a table that we just went through that shows the work function for sodium is about 2.75 and for aluminum is about 4.28. So if I want to find out what those frequencies are, I just take the work function divided by Planck's constant, and I end up with 6.64 times 10 to the 14th hertz for sodium and 10.34 times 10 to the 14th hertz for aluminum. So these frequencies, I can convert them to wavelengths very easily using C over F, so the speed of light divided by the frequency we just got, and here we get 452 and 290 nanometers respectively for sodium and aluminum. And so that works out pretty well. If I have light of light consisting of 2.7 eV photons and it's incident on a piece of sodium which has a function of 2.3 eV, a work function, they want to know what is the maximum kinetic energy of those ejected electrons. And so that's pretty easy to do. We just subtract the two and that'll give you your energy. If I want to find the maximum electron speed, here we've got an example that shows us how to do that. So they want to know what are the maximum electron speed and the stopping potential if sodium is illuminated with light of a wavelength 300 nanometers. We do remember that sodium on that chart has a work function of about 2.75 electron volts or eV. So to solve this, first I have to find the frequency. So here the frequency is about 1 times 10 to the 15th. And if I multiply Planck's constant times that frequency, I get about 4.14 eV. So the maximum kinetic energy would be that 4.14 minus the work function. That gives me 1.39 eV, which if we convert to joules would be about 2.22 times 10 to the negative 19th joules. Since I know that kinetic energy is equal to 1/2 mv squared, I can plug in, just rearrange this equation, solve for Vmax, and I have 2 times the maximum kinetic energy divided by the mass of the electron, and I get the number somewhere around 7 times 10 to the 5th meters per second. Here I have to make sure that my kinetic energy is in joules in order to calculate that speed. Now that we know the maximum kinetic energy, we can now find the stopping potential. So the stopping potential here is equal to K max over the charge. And so we should end up with about 1.39 volts. So an anode voltage of negative 1.39 volts will be just enough to stop the fastest electrons and reduce all the current to zero. Next quick check, this one wants to know what happens to this graph. So we're looking at this one at the photoelectric effect current if the intensity of the light is reduced by 50%. So we're going to reduce intensity. If we reduce intensity, then the one that would match up the best is going to be letter A. In letter B and C, we see that the stopping potential actually changed. All we want to do is change the current. So the current just needs to come down a little bit, and then we'll just leave that stopping potential right where it is, right there. If I would reduce it even more, so let's say by 75%, it might look like this, and then 100%, it would just give that flat line all the way across if I cut that light completely. They want to know what happens to the graph if the work function is slightly increased. So I'm going to increase the work function. If I increase the work function, then those electrons will emerge slower, so the stopping potential has been reduced, and the number of photoelectrons will remain the same. So even though I've changed the work function, the current will be the same, but my electrons will not have as much energy. So I can move my stopping potential over just a little bit. Here's another graph. This one is, they want to know what happens to this graph of the photoelectric current if the cathode's work function is slightly increased. So if I increase that work function, that threshold should shift to a shorter wavelength. So shorter wavelength because I've increased that work function, and that would give me a higher frequency too. In this next one, they want to know what happens to the graph of the photoelectric current if the cathode's work function is larger than the photon energy. And if that happens, then the energy of the photon is less than the work function, and I won't kick any of those electrons out. So I won't get a change of potential and definitely won't get a current as a result. The energy of a photon of red light should be blank the energy of a photon of blue light, and it is definitely smaller than. We kind of talked about that a little bit earlier. Next one, a beam of light has a wavelength of lambda. The light intensity is reduced without changing the wavelength. Which of the true after the intensity, which is true after the intensity is reduced? And here we know if it's reduced, we'll just have fewer photons. They won't have smaller photons, they won't travel slower, and they won't have less energy. There just won't be as many of them. And that is the end of the photoelectric effect.